Okay, we're going to look at two new topics, local linearity and the differential. The idea of local linearity we've already talked about at to some degree. The idea is that if you take some 3D curve and focus in on one point in that curve, that as you zoom in, that curve starts to become, the more you zoom in, becomes a plane. And this is analogous to single variable calculus when we were talking about a curve being approximated by a line locally. So finding a tangent line and finding a tangent plane. And what we're going to be talk about is finding a tangent plane, which is this idea of local linearity. So let's take this contour map, and what we can see is that this would not be a level plane because it is not straight lines. So this would be sort of like, well, let's think, if this would be like going down the least steep way. Here would be the most steep direction. So clearly this is not linear. But if we were to zoom in on this one point right here, and so let's think about zooming in on it. As we zoom in, and then zoom in more, eventually all, or pretty much most, unless there's an asymptote, so almost all shapes, as you zoom in and zoom in and zoom in, become locally linear. And so that's what we're looking at here. So we could think about zooming in on a table in the same way. Looking at this table, we can make the quick assessment that it's not linear. For example, from 1 to 4, we're going up by 3, and from 4 to 9, we're going up by 5. So that's not linear. But if I were to look at points that are incrementing by less instead of going up by 1s, we could think about going up by 0.1. So in this case, we increment by 0.9, and then we're incrementing by 1.1. So that's getting closer. And then if we zoom in on the table even more, so now we're going up by 0.01, we notice that we're incrementing by 0.06, 0.06. So we've got a consistent, and that's not 0.06, that's 0.04. So we're incrementing by a consistent amount in all directions. So 0.04, 0.04, 0.04, 0.04, and then as we change our y values, we've got a constant slope. In this case, it's 0.3 or 0.03. So going down the rows and going across the columns, we have a constant rate of change as we fix one of our variables. So this data table became linear. So here's a nice picture of what's going on. What we're saying is that this is a tangent plane, and this plane we're going to call L of xy, and it's linear. And for values of x that are close to this point, sorry, for values of x, y, z close to this point, our plane does a pretty good job at approximating the function. And we like to deal with the planes because planes are much easier for us to visualize. They're much easier for us to work with because linear functions are simpler. So what we want to be able to do is get an equation for this linear approximation. So before we do that, let's think about a problem that you were doing a ton of in single variable calculus, which is to find a tangent line to the graph y equals x cubed plus x at x equals 1. Well, to get a quick picture of that, we know that y equals x squared plus 1. So it's going to look something, let's see, I think something like that, roughly. And at x equals 1, we need to find y. Well, y would be 1 cubed plus 1, plugging it into my equation is 2. So at 1, it corresponds to 2. And then I need to find the slope here. So the slope of that line is going to be the derivative at 1. Well, the derivative is 3x squared plus 1. Evaluated at 1 is 3 plus 1 equals 4. So I know the slope, I know a y value, and an x value, so I can get my linear equation, the general one being y equals mx minus x1 plus y1. Filling in for my given case, it equals 4x minus 1 plus 2. So that's pretty simple. And really the tangent plane is exactly the same thing. We're going to find the partial derivative in the x, the partial derivative in the y, and get an equation for a plane. So given, the steps are this. Given f of x, y, what we need to do is, 1, find f of a, b, and that's our z1 value. And then we need to find partial derivative with respect to x and find the partial with respect to y. And now we're going to find an equation of a line, which we've done in the last chapter, and now just using our incorporating our understanding of partial derivatives. So our function L of xy is going to equal f partial x times x minus a plus f partial y times y minus b plus f of a comma b. So that is our equation for a tangent plane to our surface. It's in slightly different order, but it's exactly the same thing. So let's see an example of that. Let's just get a picture here of what's going on. We are looking at a graph that looks something like this. We've seen this now a bunch of times. And we're trying to find it at the point when x equals 3 and y equals 4. And when x equals 3 and y equals 4, we know that z equals 3 squared plus 4 squared, which is 25. So up 25. So there we are at the point, 3, 4, 25. So I know my point. Now I need to find the partial derivatives. Well, partial derivative with respect, the partial derivative with respect to x equals 2x, and the partial with respect to y equals 2y. And then at the given point, we're talking about f of x at 3 comma 4, which is just 2 times 3, 6. And at f partial y at 3 comma 4 equals 2 times 4, which is 8. So the equation for my tangent line would be, or my tangent plane rather, is L of x comma y equals 6 x minus 3 plus 8 y minus 4 plus my z value 25. And notice that in their solution down here, simplified it and expanded it, but you can leave it in this form. This is in point slope form, and that's fine. All right, so let me pause the video right here, and we'll get you started on another video in a second. So let's formally define this process that we were just looking at. It's called a tangent plane approximation, and what you need in a tangent line approximation is that our function f of x, y must be differentiable at the point a, b, and if it is, then we can approximate our function as a line, or as a plane rather, as a linear function. And here's this equation that we've developed. So the idea being that this right-hand side is an approximation, and that approximation is called the local linearization of f near x equals a and b. So that's just the language that we'll be using. And here's a picture to see what's going on. Just to be totally clear, and I'll try to make this clear, here's our 3D curve. And we are trying to find a local linearization at the point AB. And so you'll notice that we have this green plane, which is the local linearization of it. And the idea being that if we fix y, so here's my y-axis, if I fix y and I only change x, that increase, that change in z value is the change in x times the partial derivative with respect to x. In other words, this is like the slope times change in x, which will give you the change in y. Likewise, up here in black, this is when we fixed our x and only changed y. So that resulted in a change in z, which is simply or exclusively from my change in y being multiplied by my partial with respect to y. And then the slightly more complicated is if we look over across the way to this point here. In this case, x changed and y changed. So if I was at the same z value here, my change in z equals my change in x times the partial in x plus the change in y times the partial in y. Because the partial in x and the partial in y are telling me how much my z changes when an x or a y changes respectively. All right, so let's, we've already done this finding the local linearization, but let's now use it to estimate some points, and just to see how well it works. So if we look back to when we did this work before, we did this problem already. So let's use that equation that we already developed. And we have that the local linearization equaled 25 plus 6 x minus 3 plus 8 y minus 4. And if I wanted to approximate this point here, so L of 2.9 comma 4.2, that's going to equal 25 plus 6 times, putting 2.9 now in for x, I'll get negative 0.1 back, and putting 4.2 in for y, I'll have 0.2. So we get 25 minus 0.6 plus 1.2, which equals 25.6. Well, how did that do? How did we do it approximating it? So let's think about if we actually put these points into the real equation. So let's compare my approximation to f of 2.9, 4.2, and we'll do that on the calculator. So we got 2.9 squared plus 4.2 squared, which is 26.05. So our linear approximation did a pretty good job. But what happens when our point gets further away from 3, 4, such as 2, 2? So if we look at 2, 2 and look at our approximation, we get 25 plus 6 times negative 1 plus 8 times negative 2. So simplifying this, 25 minus 6 minus 16, which is 3. And let's see what the function actually would be? Well, f of 2, 2 is going to be 2 squared plus 2 squared, which is 8. So now, as we get further away from the point at which we did our local linearization, our L of xy, our local linearization around that point, becomes less and less accurate. So it's only accurate for values of x and y that are close to our given values. Okay, so let's look at an example when we don't have an equation, when we're looking at a table. So it says designing safe boilers depends on knowing how steam behaves under changes in temperature and pressure. So it says give a linear function approximating the volume for temperature near 500, near pressure that's 24. So we're talking about this point right here. And so the idea is we can approximate the partial derivative, the change in V partial as our pressure changes. And the way that we're going to do that is by comparing it to this point right here. So V partial with respect to P is going to be 21.86 minus 23.69 all over 26 minus 24. So if we get what that equals here, so 21.86 so that partial derivative estimation is negative 0.915. And that's saying that as pressure increases, the volume is decreasing under the same temperature. Okay, well, what about as we change our temperature and keep our pressure constant? So that's the differential, or rather the partial derivative of volume with respect to temperature. And what we see is our pressure goes up as our temperature increases. So a change in temperature increases the volume. And just to get an actual value for that, we have 24.2. So we got 0.0255. Okay, so now we have the partial derivatives, and we know the, we know the x value, the x value, the y value, and the z value using x, y, z, or rather the temperature, the pressure, and the volume. So our equation, our linear approximation, is going to be that the volume as a function of temperature and pressure will equal 23.69, that's the volume, plus 0.0255, that's this here, times temperature minus 500, minus 0.915, that's the partial with respect to P, parentheses, P minus 24. So a linear, a local linearity, and then, so that's part A, done. And it says now estimate the volume of a pound of steam at this temperature and this pressure. We'll notice that those temperatures and pressures aren't on our table, but by making this local linearity, we can approximate that volume at 505, comma 24.3. It's going to equal, well, we're just going to plug those values in. So 23.69 plus 0.0255. Now putting in 505 in for here, we'll just get 5 back, minus 0.915. And we're plugging in that in for our P, so we'd get 0.3 back. So now it's just about, plugging that into your calculator to find an approximation for the volume. So it estimates our it estimates the volume to be 23.54. So that's how you can use a table to make inferences about points that aren't given in the table by creating a local linearity and using that local linearity. So let's now do an example when we're dealing with more than just two independent variables. Let's think about that we've got some four-dimensional situation, f of x, y, z equals x squared plus xy plus z. And I want to find the local linear approximation at f of 1, 2, 3. Well, first of all, let's find f of 1, 2, 3. F of 1, 2, 3 is 1 squared plus 1 times 2 plus 3, which is 1 plus 2 plus 3 equals 6. So that's my dependent variable. And then I need to find all of the partials. So f of f partial x is going to be 2x plus y, and fy is going to be x, and fz equals 1. So plugging in my points, I'm going to get 2 times 1 plus 2 equals 4, and 1, and 1. So now that I have all that, I can get a linear approximation with 3 independent variables, which is going to equal 6. That's my f of 1, 2, 3 point, plus 4 coming from here, x minus 1, plus 1, y minus 2, plus 1, z minus 3. So there is my local linearization. Okay, so that's local linearization, and as promised, we have another topic which is called the differential, and the differential will be an extremely important topic and idea for us to understand. The differential really is just saying how much is my independent variable changing for very small changes in x and very small changes in y. So looking at our local linearization, if we were to subtract f of a comma b from both sides, on the left-hand side, I'd have f of xy minus f of ab. And this is my change in f, my delta f. And what's left on the right-hand side is my partial derivative with respect to x times the change in x plus the partial derivative with respect to y times the change in y. That's just this here. And the idea being, a key thing is that these aren't equal. They're approximately equal because our function is just an approximation. It's not exact. Remember, this is my original function, and here is my linear approximation. But for values of x and y close to a and b, if I take the change in x and multiply by the partial with respect to x, and the change in y multiplied by the partial with respect to y, it will roughly give me my change in my y, or change in my z value, change in the dependent variable. And so this idea being, here's a way that we can approximate how our dependent variable changes given a small change in x and a small change in y. and this is an introduction to a tool that we're going to be using quite a bit. This is so important that this idea that it's given the name the differential. And the idea is, if we let delta x approach 0 and delta y approach 0, then delta f will correspondingly also approach 0. So we're going to replace these, mega changes, delta x, delta y, delta f, with dx and dy and dz. So we're talking about changes on the micro level, the infinitesimally small changes. And when we're infinitely small, when these changes are infinitely small, then it actually is called the differential. And just to read it, the differential at a point A, B is the linear function of dx and dy. So that's what the differential is defined as. It's the linear function of dx and dy given by this formula here. So our differential df equals f of x ab dx plus f of y ab dy. And again, what we're talking about here, this is representing our change in z or f, whatever you want to call it. And it's all coming from the change in z from x adding to the change in z from y. Because the whole thing is we want to be able to approximate change. And so we're approximating it with our differential. That's our function that approximates change. So let's just do some computations of differentials, and that'll be it for us. So the first one, we have x squared e to the 5y. So we need to calculate their differentials. So first calculate the partial derivatives. So the f partial x is going to be 2x e to the 5y. Notice this doesn't change because it doesn't have an x in it. And f of f partial y will be x squared times e to the 5y times 5, using the chain rule to find the derivative of that there. So our differential for part A would be that df equals 2x e to the 5y dx plus 5x squared e to the 5y dy. And this equation here measures infinitely small, for infinitely small changes in x and y, it's going to predict the change in z for any x and y. Okay, let's look at B. So for B, we have to find the partial derivatives. So f partial x, using the product rule now and the chain rule. Oh, really just the product, chain rule too. So let's take the derivative of the first, which is 1, times the second, plus the first times the derivative of the second, cosine of xy, and then we have to take the derivative of the inside, which is just y, and f partial y is going to be x times cosine xy times x. Well, simplifying these a little bit, we have sine of xy plus xy cos of xy. And here we have x squared cos of xy. So our differential, df, is going to equal, and it's a little bit longer now, so sine of xy plus xy cos of xy dx plus x squared cos of xy dy. Done. Now, how about the third one? Well, I'll leave that up to you, but we're not going to do that one here. And that is the, oh no, we're not quite done yet. So here's a slightly harder differential that we're going to be looking at. It says the density of carbon dioxide gas depends on the temperature and pressure. The ideal gas model for carbon dioxide gives what is called this state equation. So here we have density as a function of pressure and temperature. And it says compute the differential dP. So what we need to do is first find the partial derivative with respect to pressure. And I think it might be easier for us if we could use quotients later on, but let's write this in terms of a negative exponent. So the derivative, partial derivative with respect to p, well, that's just going to be 0.5363p, sorry, no p, because we're taking the derivative and it's just linear, times t plus 273.15 to the negative 1. And f partial t is going to equal 0.5363 p. Now we take the derivative of this, so times negative 1 times t plus 273.15 to the negative 2, and then we have to take the derivative of the inside, which is just 1, so that doesn't really change anything. So this equals, if we now simplify these out of negative exponents, this is 0.536, let's write that a little neater, 0.5363 over t plus 273.15, and f partial t is negative 0.5363 p over t plus 273.15 squared. So the differential d rho, and that's density rho, so d rho equals 0.5363 t plus 273.15 dp plus, well, really minus, so minus 0.5363 p over t plus dt. So there we have it. And what do those coefficients, the signs of the coefficients mean? Well, dP is greater than 0, so as the pressure increases, so does the density will increase. And as the, and that's looking at the first sign, and for dt, that is less than 0, so that means that as temperature increases, our density actually goes down. And that makes sense chemically, now going into our understanding of chemical science and properties of gases. You know, as pressure goes up, we're putting more stuff into one space. We're increasing the amount of matter in a given volume. So if pressure goes up, we increase the amount of matter. If we increase the amount of matter in the same volume, density goes up. Whereas here, as we increase temperature, now things are going to start moving around faster and faster, and they're going to be further and further apart. So as you increase the temperature, that actually spreads things out, which causes the density to go down. And that is it. So we looked at two things, local linearization and the differential. Thanks for paying attention. Goodbye.